everyone. Today in my session, I will be explaining you reaction, preparation and properties of alkane. Before, before proceeding with the session, kindly go through the mind map on preparation, reaction and properties of alkane which I have uploaded on my Instagram account. Now let's get started. Now let us start with preparation of alkenes in detail. Now the first one is from hydrogenation or catalytic reduction. The best catalyst to prepare alkane from alkene and alkyne is ranitidine, which is nothing but an alloy containing nickel and aluminium digested with NaOH. The catalyst is very effective over normal temperature and it works at 200 to 300 degrees Celsius. Other catalysts commonly used besides nickel is platinum or palladium, which requires a temperature between 200 and 200 to 300 degrees Celsius. Now, the reduction of unsaturated hydrocarbons with nickel at temperature between 200 to 300 degrees Celsius is called as Sabatier-Sanderson's reaction. And then this reaction looks like this. You simply need to add hydrogen across the double and triple bond, and then the final product will be the corresponding alkane. The next reaction is from alkyl halide. You need to take alkyl halide, react with nascent hydrogen. The catalyst which you can use is zinc HCl, zinc in acetic acid, zinc copper couple in ethanol. Now the next reaction is Wood's reaction. Now when alkyl halides are treated with sodium metal in dry ether, it results in the formation of alkane having double number of carbon as that are present in parent halide. Now as you can see in the parent halide, we have taken methyl halide and then the corresponding alkane which we have, it has 2 number of carbon. Okay. That means the carbon atom gets doubled in this reaction. Now, whatever I have written in the box, it will be eliminated and then this carbon will be bonded to this carbon. So, you will be getting CH3 bond CH3. This reaction is not suitable for unsymmetrical alkanes. We can easily prepare symmetrical alkanes using this reaction. And one more important point to be noted is methane cannot be prepared by this reaction. The next reaction is Franklin reaction. Franklin reaction is absolutely same as the Woods reaction. The only difference is in place of sodium, you need to take zinc. Okay, in place of sodium, simply you need to take zinc, rest all will remain same. Now the next reaction is Corey-House synthesis. When an alkyl halide is treated with lithium, the final product we get is alkane. Now, this reaction is good for both symmetrical as well as unsymmetrical alkane. So, you can easily prepare unsymmetrical alkane using Corey-House synthesis. The next reaction is Grignard reagent. Grignard reagent, all of you know it is RMgX, where magnesium is attached to R as well as halide group. Now, Grignard reagent on treatment with compounds containing proton, which we can also call it as a protic reagent. Okay, protic agents which contains a proton. Simply this proton gets added on this alkyl group. So R bond H is nothing but alkane. Now which are the protic agents? H2O, ROH, R, NH2. Now wherever you find a proton present, that will react with Grignard reagent to give corresponding alkane. Grignard reagent reacts with alkyl halide to give higher alkanes. As you can see, Grignard reagent when treated with alkyl halide, we will be getting higher alkanes. Now the next two reactions from lithium aluminum hydride and from sodium boron hydride. Lithium aluminum hydride can reduce only primary and secondary alkyl halides. Whereas sodium borohydride, it reduces 2 degree and 3 degree alkyl halides. It cannot reduce primary halides. Now the next set of reaction is Clemmensen reaction. This reaction takes place in acidic medium. Now, since the word itself is reduction, you need to add hydrogen and remove oxygen. So, I have added hydrogen in this form, and then this oxygen will be removed in the form of water. So, the final product you will be getting is ethane, or you will be getting is alkane from any aldehyde or a ketone. Now, the simple trick that you need to remember is the carbonyl group. Okay, this is the carbonyl group which is present in both aldehyde as well as ketone. This carbonyl group, it will be getting converted to CH2. Remember this trick for both Clemmensen reduction reaction as well as for Wolff-Kishner reduction reaction. Now, for Clemmensen reduction reaction, as you can see, the CO getting converted to CH2. So, CH3, CH2, and then this one hydrogen, you will be getting ethane. Same way, this C double bond O, it is getting converted to CH2. So, the final product is propane. Same, we can apply for Wolff-Kishner reduction reaction. The medium is alkaline, and then the reagent we are using is hydrazine. So, the same concept you can apply. This carbonyl group, it is getting reduced to CH2. Carbonyl group getting reduced to CH2. So, aldehyde and ketone can be converted to alkane. The intermediate product we formed is hydrazone. Now, the next reaction is by decarboxylation. Decarboxylation is nothing but removal of CO2 from carboxylic acid. In this reaction, we will be using soda lime, which is nothing but the mixture of NaOH and CaO. Now, the role of a CaO, that is calcium oxide, along with NaOH, is that it keeps NaOH hygroscopic, okay, that is in dry form, and helps it in fusion. So, the simple trick in this reaction is this hydrogen, it will get bonded to the carbon next to C double bond O group. So, wherever you find this carbonyl group, the carbon next to this carbon will get bonded to this hydrogen. So, you will be getting CH4. Now, remember, very important note in this reaction is the alkane formed by decarboxylation contains one carbon atom less than the original acid. Now, the next reaction is by Kolbe's electrolysis. Now, during Kolbe's electrolysis, you should know the anodic and cathodic reaction. Now, first of all, this method is used to create new carbon-carbon linkage, and along with alkane, you can also use this method for preparation of alkenes as well as for alkynes. Clear? Now, reduction of alcohol, ketone, carboxylic and aldehyde by heating them with red phosphorus, okay, at 150 degrees Celsius yields corresponding alkane. Okay. Now, red phosphorus, it is used to remove iodine as a volatile Pi3. Otherwise, the reaction becomes reversible. Now, this was related to preparation of alkanes in detail. Now, let us proceed ahead with properties of alkanes. Physical properties, physical and chemical properties of alkanes. Remember, the first four alkanes are gases. The next 55 to 17 are liquids, and then the alkanes containing 18 carbon and above it are solids at room temperature. Now, based on the solubility, they are insoluble in water. Since alkanes are non-polar, as we know that like dissolves like, okay. So, since alkanes are non-polar, they are insoluble in water, because water is what? It is polar. Rather, alkanes, they are soluble in non-polar solvents. The next one is density. They are less dense than H2O. They are less dense than water, and because of that, they float on top of water. The next one is boiling point. Remember, next point is boiling point. Now, the boiling point of alkanes is directly proportional to molecular weight, okay, for N alkanes, and then they are inversely proportional to branching. Now, what could be the reason? Remember, van der Waals force, they are directly proportional to molecular weight. And then van der Waals force, they are again directly proportional to surface area. If the surface area is small, van der Waals force is small. Surface area is larger, van der Waals force is larger. So because of this branching, surface area is small. So that is the reason why van der Waals force is also small. And then ultimately boiling point is also less. So in short, wherever you find branching, boiling point is also less. Now let us take one example, pentane, hexane, heptane. Now if I look into the number of carbon, heptane, it has the more number of carbon. So the molecular weight of heptane is greater than hexane, is greater than pentane. So the same logic we can apply here. The boiling point, it is greater for heptane. So the maximum boiling point is for heptane, then it is for hexane, then it is for pentane. Same concept you can apply here for branching. As I said, boiling point is inversely proportional to branching. So if you draw the structures, N-pentane, it has a straight chain. Isopentane, it looks something like this. Okay, so since there is a branching, the boiling point is reduced. For neopentane, the structure is, this is the structure for neopentane. Now remember, you are going to write down hydrogen as well. I'm only concentrating only on carbon. Okay, you need to write down hydrogen. Now over here, as you can see, because of this branching, surface area is small. And that is the reason why van der Waals force is small. And because of that, boiling point is also small for neopentane. Okay, this is the entire concept related to boiling point. Now for melting point, remember alkanes with even number of carbon atoms, they have higher melting point than odd number of carbon atoms. Now the next very important point is knocking. Now knocking is basically pre-ignition of the fuel or air mixture in the cylinder ahead of the flame. It causes knocking. Now basically knocking, it reduces efficiency of the engine and it can also damage the cylinder and piston of the engine. Now the next one is very important and many questions have been asked on this particular topic, that is octane number. So basically octane number gives us an idea about the quality of gasoline. Now basically octane number, it is a scale which is used to determine the quality of a fuel in an internal engine. Now two pure hydrocarbons are selected as standard, N-heptane and isooctane. Now N-heptane, since it has a straight chain hydrocarbon, it knocks very badly and have octane number 0. Okay, it has octane number 0. Whereas isooctane, they are branched chain hydrocarbon and they are very good anti-knocking properties. They have octane number 100. Now, order of quality of gasoline. Remember, as the length of the chain increases, octane number decreases, and as the branching increases, this is increases, not decreases. Clear? I repeat, as the length of the chain increases, octane number decreases, and as the branching increases, octane number increases. Clear? Now the next is octane number can be increased by cracking, aromatization, and isomerization. Topic is reaction of alkanes. So let us try to understand reaction of alkanes in detail. The first one is halogenation. Halogenation is nothing but reaction with halogen, or remember the alkanes undergo substitution reaction. In this case, substitution of halogen takes place. So you can add any halogen. So if I take chlorine, you will be getting chloroalkane, bromine, you will be getting bromoalkane, iodine, you will be getting iodoalkane. Same way, if I take nitrating mixture, that is a mixture of HNO3 and sulfuric acid, I will be getting the corresponding compound as a nitroalkane. Clear? Same way, if I carry out the reaction in presence of sulfuric acid, we will be getting the final product as alkane sulfonic acid. Same way, there are few more sets of reaction. The next one is, if I take sulfuryl chloride, I will be getting chloroalkane for pyrolysis. Now, pyrolysis, it is a Greek word. Pyro means fire and lysis is nothing but loosening. Okay. So, basically, it is a thermal breakage of organic molecules. And when the process is applied to higher alkanes, it is called as cracking. Okay. Now, in this process, there is breaking of carbon hydrogen bond as well as carbon carbon bond. The next is coming to the next reaction, that is combustion reaction, complete combustion and incomplete combustion. For complete combustion, you can simply follow this formula. Remember, combustion is nothing but burning in presence of oxygen. Okay, and in this process, heat energy is released. So this reaction is an exothermic reaction. Coming to few more reaction, that is aromatization. Aromatization is nothing but preparation of an aromatic compound from alkane. Now, it is applicable to alkanes from hexane to decane. Okay, from hexane to decane, we can prepare aromatic compound. As you can see, from N-hexane, we can prepare benzene, and from, again, heptane, I can prepare toluene. Coming to isomerization. Isomerization is nothing but the, now coming to isomerization. Now, unbranched chain alkanes on heating with aluminum chloride and HCl at 200 degrees Celsius, they are converted into branched chain alkanes. Okay, so branched chain alkanes, they convert into more branched chain alkanes. As you can see, the straight chain getting converted to branched. The branched, it is getting converted to more branched chain compounds. Now, in today's session, we have studied preparation of alkanes, properties and reaction of alkanes. Now, kindly go through my video and short notes and tricks which I have shared on my both the accounts, Instagram account as well as YouTube channel, and try to test yourself. These are few questions I am sharing with you. In the next session, I will be discussing the answers with solution. Kindly drop your answer in comment box. Thank you students for watching. If you like my video, kindly like, share and do not forget to subscribe my channel. Thank you.